The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, our last speaker is Murat Saçoğlu. He's a distinguished university professor and university research chair at the University of Ottawa. He is the recipient of numerous research and teaching awards. His main interest is seismic design and retrofit of reinforced concrete structures.
Thank you, Thomas, and good afternoon. This being the last presentation, I'll be very quick. I will be presenting to you the results of an experimental research program on seismic repair and retrofit of reinforced concrete columns through transverse prestressing. And what I will present to you essentially pertain to bridge columns, but there's a companion research program underway for building columns under higher axial load. In terms of bridge columns, we face these three well-known seismic deficiencies, one being shear, the other one being lack of confinement under compression combined with flexural compression, and then lack of proper splicing in potential plastic hinge regions. And to overcome these problems, we are undertaking an unusual application of prestressing rather than in longitudinal direction, applying it in transverse direction. The uniqueness of the technique is to apply active pressure in addition to passive pressure. All other jacketing techniques, whether it is steel jacket, concrete jacket, or FRP, have passive pressures. But in this case, we're in fact able to recover some of the aggregate interlock resistance, shear resistance of concrete, because we're essentially squeezing the column as well as improving bond in the splice region. The technique is obviously well established, and we're using no new material. We're using 7-wire strands. The only thing that is challenging is the anchors. Initially, we started out using the anchors that are being used for tanks, water tanks, and then we developed a smaller size anchor, the one you see on this photograph. For circular columns, there's very little challenge because you can develop full hoop tension, but for square columns, we had to use razor discs to develop hoop tension, and hence we had to use different types of hardware. Now, here you see in a laboratory setting a student putting on 7-wire strands, and because they look like belts, we call it retro belt, and then applying prestressing or post-tensioning one by one. And this is a finished column, and obviously we don't leave it like that. I'll show you a picture of one which is shotcreted to protect against corrosion. And this is a circular column, and the picture you see on the left-hand side is actually during testing at 1% drift. And this is for square and rectangular columns. There's a fair bit of additional anchors, but we are currently using concrete pieces, precast concrete pieces as filler material, and even individual steel pieces to be able to transfer this transverse load. And this is the corrosion protection shotcreting. We used different types with and without bonding agent, without fibers, but they all behaved roughly the same. On the right-hand side, you see finally the shotcretes falling as late as 7% drift. So the performance was fairly good. In terms of field application, it only requires a two-person crew, and we are able to do this in half a day in a laboratory environment. I suspect it would go very quickly, and then you can do either rapid repair or retrofit before or after earthquake. Some of the test results here, you see a shear dominant circular column, which was able to go up to 1%, and there was a sudden failure after that, and we had 25 millimeter bars, and this is half a meter, I think 600 millimeter diameter circular column, and we used 10 millimeter hoops spaced at 300 millimeters to reflect the pre-1970s bridge practice in North America. And here is the companion column with transverse prestressing. We were able to go up to 4% drift with very little strength decay, and then it gradually started coming down. Now, this had 25% of yield strength of steel as initial prestressing. As I will explain later on, you can increase prestressing, which would increase concrete shear resistance at the expense of reducing shear reinforcement contribution. But the idea is if you use higher prestressing, then presumably after an earthquake, you would have a crack-free column. But if you approach zero prestressing, then obviously you will get these diagonal tension cracks, but then there would be extra shear reinforcement. And a similar comparison for square columns. This is again a short column, shear dominant, and when we tried to cycle at 2% drift, it couldn't take it. In fact, it failed at the second cycle. So the capacity was essentially 1%. And then there was a huge diagonal tension crack, and it fell apart. And a companion retrofitted column was able to go up to 4% drift without much strength decay, and then sustained 5 or 6% with some strength decay. Then we looked at flexure dominant columns where essentially failure mode was lack of confinement. These are again hoops spaced at 1 foot spacing, intentionally under-designed. And this time, due to the inherent ductility of reinforced concrete, even without confinement, we were able to go up to 2% drift, and then it started decaying. I have to reemphasize the fact that these are bridge columns under low levels of axial load. Under higher levels of axial load for building columns, you may not get 2% drift. And here's a companion circular column. Again, we were able to go up to 4% without any problem, and transverse prestressing seemed to work. Where it was most effective, whereas some of the other techniques, especially FRP jacketing, does not work, is square and rectangular columns with splice deficiencies. In fact, in the Canadian standard for FRP, we do not allow use of FRP for strengthening against splice deficiency. If it is square or rectangular, for circular it works, but otherwise, because of the passive pressure, it does not provide sufficient clamping force, whereas transverse prestressing does that. And here is a square column with 20 times bar diameter splicing in the potential plastic hinge region, and hence it did start slipping after 1% drift, whereas when we applied this time, we had to go up to 50% of Fy in terms of level of prestressing. Then it performed fairly well, and once again we reached 4% drift. Now, then we damaged columns and repaired them to see if it can be used as rapid repair after an earthquake. And we intentionally avoided doing anything else, but we just wanted to simply try to laterally squeeze these columns, having developed diagonal cracks. And initial phase involved shear cracking, and I'd like to show you those. I also had a circular column, but we were being greedy. I wanted to get 1.5% drift. It disintegrated. They failed in shear very, very in a brittle manner. So this is a rectangular column, and we were able to damage it at 1% drift in one direction and 1.5% drift in the other direction. And when we did that, it was damaged more in one direction. In fact, there was a somewhat strength decay, as you can see in the upper right quadrant. When we went to 1.5%, there was 20-25% strength decay, but in the other direction, we did cycle 3 times at 1% and then stopped. And then we simply patched up with grout and then started putting the retro belts and applied 50% of prestressing at H/4 spacing. And then we were able to go up to 5%, 6% with some visible damage, but it did improve quite drastically. However, we got a funny-looking hysteretic relationship because column was damaged in one direction. It never was able to recover. In spite of that, we were able to develop strength. Initial strength was 800 kilonewton. It went up to 1,000 kilonewton because it did clamp cracked concrete, and it contributed to aggregate interlock as well as providing additional shear steel because, after all, this was a high-strength prestressing strand. And then next specimen involved damaging shear-dominant column having inadequate splicing. And in this case, we looked at square column, and once again, we had this column stopped at about 1.5% drift, and then we applied transverse prestressing. As you can see, we did go up to 4% drift, maybe 3% drift without much problem, but then it started slipping because we had already broken bond. Up to 1% is okay, but the moment you go beyond 1% in damaging the column, the reinforcement starts slipping, and prestressing did help up to only 3% drift, but then, as you can see, it started slipping. So this is an ongoing research. Presumably, if it were to be used for seismic repair work, one has to make a judgment as to how much the damage incurred was. Up to 1% drift, it is okay, but the moment you go beyond that, in this kind of a situation, one has to remove the cover and perhaps epoxy inject and then prestress, or increase level of prestressing, which is something we will look at later on. In terms of design options, circular columns are easy enough because they do provide shear reinforcement as well as confinement due to hook tension. But when you do have a square or rectangular columns, you have the options. If you're only concerned with shear, which is usually not the case, because if you solve the shear problem, then it's going to fail due to lack of confinement. But you could use left-hand side configuration where you do not need to create this additional elliptical pattern, whereas if you want to do shear confinement as well as lap splice repair and retrofit, then you have to use the right-hand side configuration. Now, shear design, this time, as opposed to having only concrete and steel contributions, there is a third component, prestressing this contribution. As I mentioned earlier, prestressing does add on to concrete shear resistance because it provides clamping force, actively closes the crack, and hence improves V sub C, and I call that V sub PC, and this is simply equal to the force in the initial prestressing divided by the cross-sectional area as additional shear resistance. And then what's left over between yield strength and initial yield strength would provide, which is quite significant, which would provide additional shear resistance due to steel. So there are two components, enhancement of concrete shear resistance and enhancement of, or addition of, extra steel reinforcement. For retrofitting for confinement, then we were able to use the expression that was developed earlier, which is a function of lateral drift, axial load, and cover to core area ratio. In this case, there is no cover to core area ratio because it's applied externally, and hence we substituted the minimum value of 0.3 in that bracket and obtained this area of prestressing. And in terms of effective prestressing stress, you can go up to 1860 megapascal, but still concrete is not able to expand that much without failure, and hence we put a strain limit. We observed that transverse strains of up to 0.5% was tolerated by concrete, but we did recommend use of 0.3 so that you would first initially overcome the initial prestressing, and then you would have zero strain, and then you can go further 0.3% in transverse tension without failing concrete as it becomes more and more confined. Now, for lap splice clamping, the suggested strain value is 0.1%. Beyond that, the reinforcement loses its ability to bond on concrete. In conclusion, I can say as a result of our tests that one can use transverse post-tensioning of columns to induce active pressure as opposed to passive only, and this does tend to control diagonal shear cracks. It does add additional confinement pressure, and then it does add clamping force in the critical lap splice region. Thank you for your attention. If there is any time, I'd be happy to answer questions.
Thank you, Murat. Two questions. The first one I think is quick. The additional shear reinforcement, the term is FPY minus FPI. So you're saying you've overcome the pre-stress, but you still get the steel strength as contributing to shear reinforcement?
Well, you already used up some of the tensile capacity by pre-stressing. What's left is what you can use before it yields.
And are you concerned then about the stiffness of the strand? Because I presume you're using high-strength material, 270 KSI.
Not really. We were able to pre-stress them. They were able to function well. In terms of when you said stiffness, I thought of something else. Being able to bend was a concern. With bridge columns, because of its size, there wasn't much of an issue, but for building columns, we're having difficulty. In fact, our building column project includes high-strength steel straps as opposed to strands.
Right. I guess I'm thinking for consistency with what I believe is the ACI requirement, where shear reinforcement shouldn't be allowed to be stronger than 60 KSI, which I understand is sort of a stiffness concern of ties and not allowing cracks to open too widely.
Well, I think the limit of 60 KSI in ACI is related to the sub C expression, because almost all of our research is done with 60 KSI steel, which yields at 0.2% strain, and the feeling is that beyond 0.2% strain, V sub C starts decreasing, and that's why. But in this case, we apply, if you like, compression first, right? So by the time it relieves that compression, gets to zero strain and additional tensile strain, you do resist a lot of shear.
Okay, great. And then the second question is if you could just amplify a little bit more on the comparison of this retrofit technique with more conventional or traditionally used retrofit techniques like elliptical steel jacketing of square columns. You mentioned, the issue of shear versus confinement versus lap splicing.
That's right. Yeah. Well, there's no question that steel jacketing works. But in terms of ease in construction, this is by far easier than applying steel jacket, where you would lift up huge steel plates and weld them and pressure grout and protect against corrosion, and all of which, as high of a strength and ductility as it provides, is little bit cumbersome. We were able to get same behavior with transverse prestressing, and one of my master students did a comparison, and it turned out to be 1/4 of the price of steel jacketing and half the price of FRP.
Thank you.
Thank you.
Yes. A quick question. I presume that the couplers have been tested in pure tension. I noticed the couplers cause, because you cannot align the
Yes.
tendons, there's a slight twist.
Yes.
Does that reduce the ductility or the strength of the strands?
No, this is a very good question. We tried to minimize that eccentricity. In fact, the original anchor was made by do-it-dag. One goes on top of the other. It virtually has no eccentricity. The ends of the holes are flaring out so that it doesn't catch the edges of the strands. We didn't have any problem. Obviously, we tested them. Yes.
Professor Satsiglu, thank you for your presentation. I have a couple of questions. Do you have any concerns about friction, for example, on the opposite side of the member you are pre-stressing, not on the sides that are perpendicular, but the opposite side? And the second one, even though you will apply this to an existing column that is quite aged, but it's a small column, will you still have some creep in something, because you are considering this the active pre-stressing, so you may want to evaluate a little bit of the creep and friction losses or something.
Okay, well, this is another good question. Obviously, we were concerned with friction, and that's why we put strain gauges all around in our tests. In circular columns, we had virtually no difference between the jacking end and the far end because it was able to slip around circular column. And for square columns, there was some variation, but not too much because we used steel pulleys. We cut pulleys, and they were able to slip around the pulley. So there wasn't much of a change. The strain distribution was fairly uniform, especially after we cycled it a couple of times. It sort of realigned itself. In terms of losses, we are not pre-stressing that much. We're talking about 25% to 50%. And losses become, as you know, significant after 80-85%. So we haven't waited 30 years, but I do not expect that there would be a loss problem. Even if there was loss, even if you just put them snug tight, it works as passive system. Yeah.
Sorry, Murat. Also, just about the losses, when we pre-stress a short strand, the anchorage slip is often a large loss. But I presume because you're stressing so low, you can overextend and allow for that.
That's right. In fact, we use double jack. We push the wedge in order not to have anchorage slip. You're quite right. We pulled with one jack, we pushed with the other one, so it locked in. There was no anchorage slip.
The question is, in terms of the repair option, are you removing the cover concrete and reinstating it, or are you putting the retro belts straight onto the cover concrete?
Okay, well, another very good question. What I have shown you was intended to be used for rapid repair immediately after the earthquake. It wasn't meant to be complete repair. Complete repair you could do on existing concrete if it's not loose, obviously if there's loose concrete. But anything less than 1% drift or column that has not suffered more than 1% drift, you do not have too much problem in the cover concrete. You can apply it directly on the cover. But if you go beyond that and if you start losing cover, obviously you have to patch it up. And if there is permanent deformation, you have to jack it back to where it was and then apply retrobelt.